Okay, Chapter 11 looks at Lewis structures and takes them a step further and looks at main group electron geometries and then more specifically molecular geometries. And that will be important to help us understand if the molecule is polar or nonpolar. We're also going to look at orbital hybridization. So when, carbon and hydrogen bond, we can sort of conceptualize that hydrogen brings in its 1s orbital, which is half full, overlaps it with the s and p orbitals of carbon to create a bond. But the s and p orbitals on carbon, they don't stay separate s and p orbitals, they hybridize. So they kind of morph into what's called an sp3 hybrid or sp2 or sp, depending on what kind of bonds are going on. So that's what we're going to look at. And then what will happen in the next chapter is, now that we have a pretty good footing on molecular structure and whether or not a molecule will be polar or nonpolar, we'll look at what are called intermolecular forces, which are different for polar and nonpolar molecules. So the chart that I have up here now is on page 2 of the Chapter 11 notes. And this notation, what we're looking at is the number of bonds, X, and it can be single, double, triple bonds, that part doesn't matter. And then E for electron pairs. And when we assign the VSEPR geometry, we're just looking at the center element. So we're going to apply this notation, AX or AX2 or AX, whatever it is, this VSEPR notation to the center element. And then that's going to help us understand what the geometry looks like. And then from there, we'll take on whether or not the molecule should be polar or nonpolar. So far we've looked at whether a bond would be polar or nonpolar. But now what we have to look at is whether the overall molecule would be polar or nonpolar. So what I'm going to do is kind of keep referring to this particular chart, but I'm going to go and look at the Chapter 10 and 11 worksheet. And we had done the first half of this for Chapter 10, looking at Lewis structures, formal charges, trying to come up with the best structure. We talked about resonance. Now what we're going to do is apply the Chapter 11 material, which is looking at the electron group and molecular geometry, and then whether or not the molecule would be polar or nonpolar, and then talk about the orbital hybridization that we get there. So the compound that we first started with was N2O, dinitrogen monoxide. And I highlighted in yellow, after formal charges, what we think is the best structure. So we ended up with a triple bond between the two nitrogens, nitrogen on the end with a lone pair. So it comes in with 5 valence electrons. We've assigned it 1, 2, 3, 4, 5 electrons, so formal charge of 0. Center nitrogen comes in with 5 electrons as well, but this time we've only assigned it 1, 2, 3, and 4. 5 minus 4 gives it an overall formal charge of +1. And then the oxygen on the end comes in with 6, but we've assigned it 1, 2, 3, 4, 5, 6, and 7. So when you're assigning your electrons for the formal charge, not the octet rule, but just for the formal charge, you do 1 for each lone electron and then half of each bond, right? So each bonding pair, 1 goes to one element, 1 gets credited to the other element. So just looking at that oxygen, it's been assigned 7 electrons. So 6 minus 7 gives it the formal charge of -1. And overall, the formal charges should go to 0 if you have a neutral compound. And what we said was the negative formal charge should always go on the more electronegative element. And so we had actually started with 2 double bonds with this molecule, but the negative formal charge on the less electronegative nitrogen would not be correct. We want it to be on the more electronegative oxygen. So this is the structure we ended up with. I had mentioned the formal charges are nice. It helps us understand bond energies, but it won't change the geometry. So in a sense, it doesn't matter too much anyway. So if I'm looking at my molecular geometry chart, what I have in bold, right, these are the main electron geometries. And what we can look at is we either have 2 attachments, 3 attachments, 4, 5, or 6. And these are the main groups. So 2 attachments, you can kind of imagine you've got a center element and X on either side, so linear. If you have a center element and 3 attachments, we're going to end up with trigonal planar. AX4 is called tetrahedral, and trigonal bipyramidal for AX5, and then AX6 is octahedral. Now within this, if some of those bonds, like the bonding X elements, are replaced with a lone electron pair, then that's going to change the geometry, the individual molecular geometry, like the more specific molecular geometry. So what I have highlighted in bold, those are the main groups, right? The like kind of under that umbrella of AX4, you can have tetrahedral, trigonal, bipyramidal, or angular, also called bent. Right, so AX4 is like the main electron group, and then the specific molecular geometry could be tetrahedral, trigonal, bipyramidal, or bent. All right, so we're going to look at an example of each of those molecular geometries in this worksheet. All right, so the first thing that we were looking at, the N2O. If I look at my center nitrogen, right, this geometry notation always for the center element, your center element is just element A, right, nothing specific. Now the X is how many bonding elements we have. Again, doesn't matter if it's a single bond, double bond, triple bond. So I've got 1, 2 bonding elements, an oxygen and a nitrogen, so AX2. And then for that center nitrogen, there's no electron pairs. So no lone pairs on the center nitrogen. So there's no E, right? There's no capital E in terms of this geometry here. So what we can see is with an AX2, this should be a linear molecule. And so what I did is I took the sort of balls and stick models that we're going to play with in lab. The nitrogen is the blue atom. You can see there's a triple bond here. So 1, 2, 3 triple bonds between the nitrogens. And then this oxygen here at the end in red. And if you look, right, that is a linear molecule. It's in a nice straight line. There's no, it's 180 degrees, right? So nice linear molecule. And when it comes to whether or not the molecule would be polar or nonpolar, in this case, what we're looking at is we have a more electronegative oxygen pulling electron density in its direction, not being equally offset by an oxygen on the left, right? This is a nitrogen on the left. It's not as electronegative. So the red oxygen here being more electronegative is going to make this electron density around the nitrogen, it's not going to be evenly distributed, right? So overall, we're going to have a partial negative end and a partial positive end. And we remember that terminology from intro and from previous chapters. That will make this molecule polar. So this is going to be a polar molecule. Now, in the case of the orbital hybridization, what we're looking at here is when we look at nitrogen, nitrogen can't expand the octet. We talked about the reasons why. It's a row 2 element. So it starts out with an S and then 3 p orbitals, right? That's what we're used to before we do any kind of bonding. When we were just looking at Lewis structures and orbital diagrams, we have an s orbital and 3 p orbitals. But in order for this bonding to occur, we need bonding sites, and each one of these orbitals, right, they're up for overlap in terms of the bonding sites. And what this morphs into is because there are going to be 2 bonds here, we need 2 hybrid orbitals. And then because we've got a triple bond here, we're going to have those bonding sites at higher energies. So these are called sigma bonds, and then these are called pi bonds. So pi bonds are when you have double or triple bonding. They're pictured beautifully in your book. I'm going to show you in just a second. And sigma is like when you just, I always remembered sigma for single. So the 2 S's go together. So if you have just single bonds, right, it's going to be a sigma bond. And then the pi is when you're adding to that single to make either a double or a triple. If it's a double bond, it has a sigma and a pi site. If it's a triple bond, it would have a sigma and 2 pi bonding sites. So in your textbook, the one that I pulled up here is the triple bond. So you've got like your sigma bond here. Now this shows 2 carbons, don't worry about that, but because it's a triple bond, so it works the same way with the 2 nitrogens. You've got a sigma bond here in purple, and then these pi bonds, there's one here and then another one here, so 2 pi bonds. And that's a triple bond. So that's like what we have here with our like balls and sticks. So you can almost imagine this as being the sigma bond, and this would be a pi bond and then a pi bond. So in terms of the orbital hybrid, because we have two attached elements, we need two sigma bonds, right, for those first two bonding sites. And then because we've got a triple bond here, we need two pi bonds for that bonding site. But the biggest, I think the easiest way to remember this is whenever you have an AX2 with the two bonding sites, the orbital hybrid is you need two. So it's going to be an S, one S and one P. That's sort of what this notation is right here. We need those two basic bonding sites for the two bonding elements, one nitrogen, one oxygen. Don't worry so much about the pi. And because there's those two orbital hybrids there, that is going to be one S and one P. All right, and then the other two P orbitals, they, like I said, they stay higher in energy. They don't lower in energy. They stay higher in energy because those are the pi bonds. All right, so I'm going to erase this really quick. And then I'm just going to note it's an sp orbital hybrid. And I'm going to make a notation that the single bond, so the NO is a sigma bond, right? It's a single bond. And then the N triple bond O, or sorry, N triple bond N would be a sigma and then two pi bonds. All right, so the overall hybridization though, when it's asking for a hybrid, is sp. And basically what we're going to do to help us remember this is, and this is what I did, is that anytime when you have AX2, it's going to be an sp hybrid, always, because you need those two bonding sites. So you take an S and you take a P, and there's your hybrid. All right, so that is your dinitrogen monoxide molecule, N2O. All right, nice linear molecule. Next one we have is the boron trifluoride, BF3. And we said that the BF3 was an exception to the octet rule. Boron often only does 3 bonds, so it doesn't complete the octet. And what you end up with here is, because there's no electron pairs around the boron, no lone pairs, just those 3 bonded fluorines, right? This notation here, you would have an AX3, right? So imagine A is the boron, and you have 3 bonding fluorines, so X3. And again, no lone pairs on the boron because it is an exception to the octet rule. So no E. All right, now in this case, the idea is that I have each of these fluorines sort of max distance away from each other, because this bonding pair repels against this bonding pair, which repels against this bonding pair. So they want to maximize the space between them. And when you have an AX3 and all of the bonding elements are exactly the same in terms of electronegativity, they're the same elements, so same electronegativity. The idea is that this electronegative fluorine is pulling down, and these electronegative fluorines are pulling up and away. And because these are all max distance and equally distance away from each other, because all 3 fluorines, right, all 3 attachments are fluorines, overall this is going to be a non-polar molecule. So the rule is that whenever you have an AX3, an AX2, AX4, AX5, AX6, when there's no lone pairs, if all bonding elements are the same, the terminal elements, if they're all the same, it will be a non-polar molecule. So BF3 is actually non-polar. It's interesting though, because if you just looked at the bond, you would say, well, wait a minute, that's a polar bond, right? Because fluorine is more electronegative. That's true. But now what we're looking at is the overall for the molecule. And this kind of always reminded me of physics. Like if you have a force pulling in this direction and a force pulling in this direction, right? And we're looking at 120 degrees, equal distance, right? And the same force pulling up and out, right? Overall, that pull is going to be evenly distributed around the molecule, and it's going to create overall nonpolar. So the rule is that if you have an AX3 with no lone pairs, or AX anything, all right, 1, 2, well, not 1, 2, 3, 4, 5, 6, and there's no lone pairs and all those bonding elements are the same element, overall it will be nonpolar. Now, in terms of the orbital hybrid, now we need 3 bonding sites, right? So we're going to take an S and 2 Ps. So whenever we have an AX3 geometry, it will be an sp2 hybrid. We need 1 S and 2 Ps, right? So 1 S and then 2 Ps for those 3 bonding sites. So this geometry is called trigonal planar, and it makes sense, trigonal, right, like a triangle, and it's in a plane, right? It's nothing is sticking up or out. This is just a nice planar molecule, and trigonal makes sense because it looks like a triangle. So that's trigonal planar, sp3. All right, and that would be the boron trifluoride. All right, so let me write that, trigonal planar. All right, then the next molecule we have is the nitrate. So the next polyatomic ion, I should say. All right, and what we had with nitrate, with our formal charges, we ended up, well, the formal charges here, we couldn't make any better. We had a +1 on the nitrogen, a -1 on 2 of those terminal oxygens. And we couldn't move a lone pair on the oxygen to become a bonding pair because nitrogen cannot expand the octet. So the only thing we can do here is just understand that the formal charges all equal -1 because it is a polyatomic ion with a -1 charge. And we can't make these any better because nitrogen can't expand the octet. There is resonance allowed here, right? We talked about that in the last video for chapter 10. So when we look at this in a chapter 11 way, when we look at the geometry, we have our center nitrogen, and we have 3 bonding elements, AX3. And again, it doesn't matter if it's a double bond or a single bond in terms of this notation. There are 3 bonds, right? So it's still AX3. And no lone pairs on the center nitrogen, right? And whenever we do this geometry, just remember we're always just looking at the center element. So we have 3 bonding sites, there's my X3, and there's no lone pairs on the nitrogen, so no E. All right, so when I made this one, right, I changed the color from blue to black, but it doesn't matter. So I've got 1 double bonded oxygen, and then the other 2, right, are just the single bonds, just like we have here. So there's the double bond, single bond, single bond. And if I look at that and compare it to the boron trifluoride, it looks exactly the same. Yep. So it's in a nice plane, right? And that right there, again, that AX3, that is always going to be trigonal planar. All right. And we expect, again, like we were talking about with the boron trifluoride, because the oxygen is pulling with a certain amount of electronegativity up and these 2 out, and this is the exact same bond angle all the way through. And right, we've maxed out the space with that electron pair with the bonding, right? That's what VESPR stands for, valence shell electron pair repulsion theory, making these bonding electrons spread out as much as possible. Overall, this molecule should be nonpolar. And I always thought that was kind of a weird thing to think about, honestly, because it's a polyatomic ion, and so it's sort of odd to assess whether an ion is polar or nonpolar. So I wouldn't ask, honestly, because it's an ion. I would, and we only do polar, nonpolar with covalent compounds. So I wouldn't ask you if this was polar. I would ask you for the boron trifluoride, but it seems wrong to ask if the ion is polar for some reason. But the electron distribution should be even around the polyatomic ion. In terms of the hybrid, it would still be sp2, right? Just like we saw with the boron trifluoride, 3 bonding sites. In this case, though, there would be 1, 2, 3 sigmas and then 1 pi bond. All right, so when we have that sp2, 3 bonding sites, it's saying that 3 of those are sigma, and then the double bond is the pi bond. But the sp2 hybrid, this is what we're looking at, the 3 sort of sigma bonds there. All right, then the last one on the page is carbon tetrafluoride. And what we end up with here is finally something that's not planar. So I've got my carbon here, and then I've got 4 bonding fluorines. And instead of it being like in a straight line, like I pictured here, 2-dimensionally, that would create bond angles that are only 90 degrees. And what we can do is we can repel that a little bit better. Now your bond angle is about 109, 110 degrees rather than just 90. So they get to spread out a little bit more, but of course this is three-dimensional, right? It's not in a plane anymore. And what we look at here for the geometry is we have an AX4, right? 4 bonding sites, again, no lone pairs. All right, and this AX4 is called tetrahedral. All right, that's the name of that electron group, right? So when I look at my chart, AX4, the main group there, tetrahedral. All right, and as you would expect, now I need 4 bonding sites. So we're going to take an S and 3 Ps. So in terms of the orbital hybrid, it'll be sp3. Now just kind of to make clear here that AX2E, because it's under the AX3 notation here, this is still sp2 hybrid, right? So the main group, linear, trigonal, planar, there's my orbital hybrid. The subgroups, the specific molecular geometries where there's a lone pair, same orbital hybrid. All right, so tetrahedral, sp3. All right, and then whether or not it's polar or nonpolar, again, when you have an AX 2, 3, 4, 5, or 6, no lone pairs, and all of those bonding elements, the terminal elements, they're all the same. Overall, the molecule will be nonpolar. All right. So what I'm going to do is I'm going to pause here and then make the new models for the next page and come back and do page 2.